Picture this. You're sitting in a window seat at 30,000 feet, just cruising through the clouds.
Right. Nice and relaxing.
Exactly.
Yeah.
And you're playing this highly detailed 3D video game on your phone, and your phone is plugged into that little electrical outlet in the seat right in front of you.
So you've got three completely distinct physical and digital experiences, like all happening at the exact same moment.
Yeah, you have aerospace navigation systems actively guiding that massive plane to its destination, a digital software universe rendering a vibrant game right in the palm of your hand, and the physical electrical current moving through the wiring to, keep your battery alive.
It's wild when you put it like that.
Right, because on the surface, flying a plane, running a game engine, and charging a battery, they just seem totally unrelated.
But under the hood, they were actually driven by the exact same hidden mathematical engine. Every single one of those systems relies on an identical structural language.
And that is our mission for today's deep dive. We are unpacking this really fascinating stack of materials covering matrix operations and their real-world engineering applications.
It's a great topic.
We are going to explore how matrices serve as the foundational logic for, well, almost everything in our modern world.
Which is, I think, an incredibly empowering shift in perspective. When most people look at a matrix, they just see this intimidating, bracketed grid of numbers.
Oh, absolutely. It just looks like a wall of impossible calculus.
Yeah, but a matrix is actually just a highly efficient way of organizing and executing massive amounts of information simultaneously.
Like a really good filing system.
Exactly. It's less about doing a single, incredibly difficult math problem and much more about structural behavior. It's a mechanism to map an input to an output across highly complex systems without losing track of all the moving parts.
But I feel like before we can explore what these grids actually do out in the world, we need to understand the basic grammar of this universe, right?
Yeah, we have to lay the groundwork.
So how do these blocks of numbers actually interact with one another?
Well, you can think of it like learning sentence structure before trying to write a novel. In matrix theory, the absolute simplest sentence structure is matrix addition.
Okay, addition. Sounds easy enough.
Right, but if you want to combine two matrices, the math requires what's called an element-wise mapping.
Element-wise, meaning what exactly?
In plain English, it means you take the number in the top left corner of your first grid, and you add it directly to the number in the top left corner of your second grid.
Oh, good.
Then you just do the exact same thing for the top right, the bottom left, and so on.
So imagine stacking two ice cube trays on top of each other.
That's a great way to visualize it.
Yeah, so if one tray has 9 slots arranged in a 3x3 square, and the other tray has 16 slots in a 4x4 square, they simply won't fit together.
No, they'll just sit awkwardly on top of each other.
Right, you can't combine them. The dimensions have to be perfectly identical, so every single cube has a matching partner.
Exactly. That physical constraint dictates what operations are even possible. You simply cannot add matrices of different dimensions.
That's a hard rule.
It is. And we see a really similar structural rule applied to scalar multiplication, which is when you multiply an entire matrix by a single standalone number.
Okay, so instead of adding two different ice cube trays together, scalar multiplication is like saying, I want to double the size of every single ice cube in this one specific tray.
Spot on. It uniformly scales the entire space spanned by the matrix. So every individual entry expands or contracts at the exact same rate based on that single scalar number.
Okay, addition and scaling makes sense, but the materials point to a heavier hitter, right?
Oh, yeah. The operation that fundamentally runs the modern engineering world is matrix multiplication.
Which is when you multiply a whole grid of numbers by another whole grid of numbers.
Exactly.
And this is where, looking at the sources, the simple arithmetic kind of stops and things get a little strange.
They get very strange. Because when we multiply two matrices together, we aren't just scaling things up or combining slots anymore. We are actually combining complex sequences of actions.
Sequences of actions?
Yeah. Matrix multiplication represents the composition of linear transformations.
Right.
And because we are combining sequences of actions, the rules completely change.
Right, because the source material explicitly says matrix multiplication is non-commutative.
Yes.
Meaning multiplying matrix A by matrix B will give you a completely different result than multiplying matrix B by matrix A. Why does the order suddenly matter so much here?
Well, because it's a sequence. That structural constraint is fascinating because it goes against the basic arithmetic we learned as kids, right? Like 3 times 4 is always the same as 4 times 3.
Exactly, that's what I was thinking.
But it makes perfect sense when you realize these grids aren't just static numbers. They are active transformations.
Oh, like, okay, if I put my shoes on and then put my socks on, I get a fundamentally different physical reality than if I put my socks on first and my shoes on second.
That is the perfect analogy. The order of operations radically changes the final state.
It's not just different numbers, it's a different outcome.
Exactly. And beyond the sequence, matrix multiplication is strictly governed by what is called the inner dimension constraint.
Okay, the inner dimension constraint. Let's unpack that.
So when you multiply two grids together, you compute the new numbers by taking the dot product of the rows from the first matrix and the columns of the second matrix.
Rows from the first, columns from the second.
Right. And because of how that alignment works, the number of columns in your first matrix must perfectly equal the number of rows in your second matrix.
So they have to interlock.
Yes, like puzzle pieces. If those inner dimensions don't match, the structural laws of that mathematical space break down entirely. The multiplication is literally undefined.
Man, that non-commutative rule. The idea that the order of operations fundamentally alters reality, it isn't just an abstract mathematical quirk.
Not at all.
It is the exact mechanism that keeps an aircraft from tumbling out of the sky, which blows my mind.
It's incredible, right? Navigating a spacecraft or an aircraft through three-dimensional space is a perfect real-world application of this.
Because in aerospace engineering, specifically kinematics and attitude dynamics, systems are constantly tracking an object's orientation relative to the Earth.
Exactly. And engineers use what are called direction-cosine matrices or rotation matrices to track that movement.
Okay, so when a plane is flying, it maneuvers around its body axis, right? It yaws left and right, it pitches its nose up and down, and it rolls its wings.
Yeah, yaw, pitch, and roll. Those successive angular updates are mathematically modeled by compounding operations.
Compounding operations, so adding them up.
Multiplying them. Every time the plane moves, a new rotation matrix is multiplied against its current state.
Let's visualize how the math actually enforces this physical reality for you listening. Imagine you are holding a small toy airplane.
Okay, I'm picturing it.
If you pitch its nose up 90 degrees and then you yaw it to the left 90 degrees, you're now looking at the belly of the plane, right? And the nose is pointing to your left.
Right. You executed sequence A, followed by sequence B.
But if you start over, hold the plane flat and reverse the order. So if you yaw the plane to the left 90 degrees first and then pitch the nose up 90 degrees, the plane is now pointing straight up at the ceiling, and you are looking at the top of the wings.
Completely different.
It ends up in a totally different orientation in physical space just by swapping the order of the exact same two movements.
And the math rigorously guarantees that outcome. When an aerospace system calculates the total orientation change, it multiplies the rotation matrix for the yaw by the rotation matrix for the pitch.
Because of that non-commutative rule.
Yes. Because matrix multiplication is non-commutative, the flight computer understands that doing the yaw first creates a totally different total rotation matrix than doing the pitch first.
Wow.
The mathematical engine isn't just loosely describing the plane's flight path, It is strictly enforcing the rigid rules of 3D reality, so the autopilot knows exactly which way is up.
So we see how this strict ordering governs massive physical objects navigating macrospace. But what's really incredible to me is that if you zoom all the way down to the microscopic level, these identical compounding actions are what keep our electronics functioning.
Oh, absolutely. Moving from the sky to the hardware itself.
Yeah.
In electronics engineering, specifically circuit analysis, professionals deal with these tangled webs of resistors, capacitors, and inductors.
Which sounds like a headache.
Oh, it is. Trying to calculate the flow of electricity through a massive linear circuit network using standard algebraic equations or calculus is a nightmare of complexity.
So how do matrices help here? The materials mentioned, engineers bring these massive networks down into smaller, cascaded two-port networks.
Right. A two-port network is essentially a chunk of the circuit treated as a black box.
A black box.
Yeah, it has an input side where the current enters and an output side where the current exits. And the behavior of that specific black box is defined by transmission parameters, sometimes called ABCD parameters.
ABCD parameters.
Exactly. These parameters form a matrix that maps the input voltage and current directly to the output voltage and current.
Okay, I think I understand isolating a single component into a clean little matrix. That makes sense?
Sure.
But if I have a giant, complicated circuit made of hundreds of these components strung together in a row, It just feels like turning an electrical engineering problem into an endless math homework problem. Like, how does putting all of this into matrices actually save an engineer time?
That's the best part. It replaces the need to solve simultaneous differential equations for the entire system at once.
Wait, really? How?
Think about how a circuit physically operates when components are connected in a series cascade, meaning one right after the other.
Okay.
The physical output current of the first component instantly becomes the input current for the second component.
Oh, the end of pipe A is the exact beginning of pipe B?
Exactly that. So mathematically, you don't have to trace the current through every single twist and turn of the wire.
You just multiply them.
Yes. The overall transmission matrix of the entire massive system is found simply by multiplying the individual component matrices together.
That is so cool.
Right. The input matrix of the whole circuit equals matrix 1, multiplied by matrix 2, multiplied by matrix 3, all the way down the line.
It is incredibly elegant. You turn a chaotic reality of physical hardware into a clean, linear pathway.
It really is.
You just multiply down the line, and you instantly know how the electrical current will behave at the very end of the circuit board.
Matrices take the staggering complexity of physical systems and make them perfectly scalable, which is a crucial capability when we look at the software running on top of those electrical circuits.
Right, so we've built the physical hardware using these cascaded matrices, but the digital universe running on that hardware, like the video game you were playing on the plane, is driven by the exact same engine.
It is. Now we are talking about computing and computer graphics.
The materials refer to this as coordinate pipelines.
Yeah, coordinate pipelines.
Yeah.
Because in a 3D game world, every single leaf on a tree, every shadow, every character model, it's all defined by vertices in digital space.
Raw points of data.
Exactly. And to move through that digital world, the game engine has to constantly process those 3D assets. It has to scale them, rotate them, and translate their positions before it can project them onto your flat 2D screen.
And doing this requires specialized 4x4 matrices using homogeneous coordinates, right?
Yeah, homogeneous coordinates. Because moving an object across a digital room, which is called translation, can't be done cleanly with a standard 3x3 matrix.
It just doesn't fit.
Right. The math requires that fourth dimension in the grid to calculate the linear movement without distorting the object itself.
The scale of this is just hard to wrap your head around. I like to think of a modern graphics processing unit, a GPU, as a massive automated assembly line in a factory.
That's a really good way to look at it.
You have millions of these vertices, these raw structural points of the 3D world, just moving down the conveyor belt in parallel.
And each matrix operation in the graphics pipeline acts as a specialized station on that assembly line, stamping a very specific modification onto the vertex as it passes through.
The pipeline equation follows a really rigorous sequence, doesn't it?
Very rigorous.
Like a raw vertex comes down the line. First, it gets multiplied by the model matrix, which places the character or object into the game's broader 3D world.
Right. Then it moves to the next station, getting multiplied by the view matrix.
And what does that one do?
That transformation adjusts the object's position relative to wherever the player's virtual camera is currently looking.
Okay, got it. Finally, it gets multiplied by the projection matrix, which takes all that rich 3D data and flattens it with perspective so it actually makes sense on the 2D glass of your phone screen.
Exactly. Model, view, projection. That sequence of matrix multiplication happens for every single visible point of light, literally millions of times a second.
Millions.
Every time your character takes a single step forward, the GPU is executing that exact compounding cascade to redraw the entire universe.
Hundreds of millions of mathematical operations per frame, running at 60 frames per second. It is a testament to the unbelievable efficiency of matrix operations.
It truly is.
Because the data is locked into these standardized grid structures, computers can execute these multiplications with blistering speed.
But, operating at that blistering speed introduces a pretty significant vulnerability.
Oh, for sure.
If an engine is executing billions of multiplications a minute, doing the math wrong even once can cause the entire system to collapse.
Which brings us to the practical implementation of all this theory, the code that binds the math to the machine.
Because theory is wonderful on paper, but engineering requires safety nets.
Right. The materials detail how developers actually build standalone computational scripts to initialize these matrices and critically execute validation checks before the math is actually processed.
Yes. Software engineers utilize custom exception handlers to capture invalid structural inputs. The code actively monitors the dimensions of the matrices being pushed through the system.
It's acting like a digital nightclub bouncer standing at the door of the GPU.
I love that, the bouncer at the club. And this connects perfectly back to the very first rule we discussed, the interdimension constraint.
The physical pipe fitting we mentioned earlier.
Exactly. The number of columns in the first matrix must match the number of rows in the second matrix.
So the bouncer at the door is constantly checking the IDs of the data packets. It verifies the internal dimensions of the matrices.
Yep.
If a glitch occurs and, say, a 3-column matrix tries to multiply with a 4-row matrix, the inner dimensions don't match.
The IDs are fake.
Exactly. The ice cube trays don't fit together.
And if that mismatched data were allowed to proceed, the mathematical operation would be fundamentally undefined.
It would just break.
Completely. So the bouncer catches the error, throws an exception, and halts the operation entirely before the software attempts an impossible calculation.
Because if the bouncer fails and that undefined math sneaks into the club,
The structural integrity of the entire system fails. Yeah, in the context of a video game, the application simply crashes to your phone's home screen.
annoying but not deadly.
Right. But in an electrical network simulation, it outputs catastrophic hardware failures. And in an aerospace navigation system, an undefined rotation matrix could cause the flight computer to freeze or output corrupted telemetry data while traveling at 500 miles per hour.
That one simple rule ensuring the inner dimensions match is the absolute safety net for modern engineering software. It ensures that the structural integrity of the mathematical engine aligns perfectly with the physical reality it is trying to control.
It really is a remarkable journey from abstract theory to applied reality. We started by looking at seemingly intimidating grids of numbers and uncovered that the simple rules governing their dimensions are actually grammar of the physical world.
It's huge. We saw how the non-commutative nature of these grids, that ironclad rule that order matters, allows aerospace systems to accurately track a plane pitching and yawing through the clouds.
We explored how cascading matrices allow electronics engineers to instantly calculate the behavior of massive electrical networks without tracing every individual wire.
And we unpacked how computer graphics engines use rigid coordinate pipelines to render entirely new 3D universes on our screens, running millions of times a second, all guarded by custom exception handlers checking the math at the door.
Matrices really act as the ultimate universal translators. They take a highly complex input, an electrical current, a spacecraft's trajectory, or digital vertex, and they map it flawlessly to a new output based on a structured sequence of rules.
Yeah.
They evaluate compounding transformations, enforcing the reality that doing action A before action B yields a fundamentally different state than doing B before A.
Which leaves you with a lingering idea to ponder as we wrap up this deep dive. We've spent this entire time looking at how matrices map physical hardware and digital software.
Right.
But if a matrix is ultimately just a mechanism to evaluate a sequence of compounding transformations based on structural constraints, what other invisible systems in your own life operate the exact same way?
That's a deep question.
Think about your daily decision-making pipelines, the sequence in which you choose to execute your day. Doing action A before action B fundamentally alters the reality you're
It
experiencing.
really does.
It raises a fascinating question. Are our own lives, our daily habits, and their compounding outputs over time really just complex matrix multiplications waiting to be decoded?